This is the final part of this series about an alternative interpretation of physics. One where the universe is local and real, has an infinite scalar dimension, where space-time is real, and everything is fundamentally just motion. As an idea, it would best be described as fluid dynamics in 5 dimensions with space-time as the medium. I hope it was made clear, but I wasn't trying to attack or undermine anyone's confidence in science. The standard model of physics, as described by general relativity and quantum mechanics, is good science. As physicists are doing their best to observe, analyze, and model the universe as accurately as possible. I was merely trying to explain an alternative interpretation that I am quite fond of. I just think this idea is neat and wanted to talk about it. But I will freely admit that it's very likely wrong. This is just speculation after all. Although there may be some good reasons for discussing it. First, the universe isn't completely described by general relativity and quantum mechanics. While they work extremely well at describing the universe, there are still gaps and inconsistencies that point towards something unknown beyond our current understanding. This is known about by physicists, but solutions have yet to be found. Which is why it may be worthwhile to consider alternative ideas, if for nothing else than to poke and prod at the boundaries of what is currently known and believed. Beyond that, I do think there are strengths to the idea I have presented. For one, it requires introducing very few unknown or speculative phenomenon to work. All that is necessary is that an infinite scalar dimension exists. But this is just a consequence of the universe being infinite in size, something for which there is actually evidence for. Beyond that, I speculate that spacetime is the medium from which everything is made, and through which interactions occur. That spacetime actually exists as a real physical entity with real properties. Almost every other claim that I have made in this series comes largely from just assuming these two things are true, that the universe is infinite in scale, and that spacetime is real. And together this would mean that everything is fundamentally made from the motion of spacetime. And very little of this, at least in concept, requires denying our current understanding of physics. For the most part, it just means interpreting some results differently. It's true that I think all variations of Bell's inequality experiments are flawed, but this is just an expansion of a criticism that already exists within the scientific community, that these tests require statistical independence for local particles. All I did was try to imagine what a real and local particle would actually do within these experiments, and the expected results appear to be the same as for a non-local theory, which means that it aligns with the experimental results. And I don't think that the universe is homogeneous as is assumed under the consensus opinion. Instead, I think that the universe is structured like a fractal, because there's a flaw with the experimental design being used to prove homogeneity, which is actually a known design flaw that is acknowledged among researchers in the field. I just think that since we have so far only seen fractal structure where we can properly measure, that it's very likely that the universe will continue to have fractal structures beyond what we can observe. The most outrageous claim that I've made in this series is that quantum fields, including the Higgs field, don't actually exist. But this is just an implication of the universe having an infinite scale. It would mean that quantum fields only exist to mathematically describe particle movement from the perspective of a physicist at our scale. If an infinite scale exists, if humans are not the center of existence, then these fields have no reason to physically exist. And this is the major disagreement between the standard model and the interpretation I have presented. The standard model assumes that physicists are at the center of existence, and then draws conclusions from that perspective. I've made reference to this fact before. From the way that the fundamental constants are interpreted, the cosmos is looked at, and from how quantum field theory was built. But my alternative is that we are in a nondescript location in an infinite expanse of the universe. I believe that this is a much more scientifically sound assumption to make about the nature of the universe. And in this final segment, I will discuss why I think that is. To better explain my perspective, I'm going to spend some time talking about the heliocentric model of the universe. I know it's cliché to bring up, but it's really good at demonstrating 2 key points. First, that just because an idea is good at making predictions doesn't mean that it's entirely correct. As even though a heliocentric model is an accurate description of reality, the early models of Copernicus and Galileo were much less accurate at making predictions about planetary motion than the contemporary geocentric one. Discussing how this can happen will help to illustrate what it means to analyze and interpret observations of the universe. In this case, it comes down to the intent of these two models and how they both approached their ideas. For Copernicus, he was just exploring what it would mean for the Earth to be in motion. This line of thought led him to a heliocentric model, as it offered explanations for a number of phenomena, like why there were seasons on the Earth, or what causes retrograde planetary motion. Galileo created his model based on a number of observations he made with the more accurate telescopes made in his time. These include the way that shadows moved over other planets and the Moon, and the discovery that some planets had moons of their own. Galileo reasoned that the best way to explain these observations would be for the Sun to be at the center of the solar system and the Earth just another planet that orbits around it. In both cases, they were trying to understand how the universe works, either by reasoning out how things could be or by trying to make sense of observations that seemed incongruous with the current model. And this led to the correct answer that the Earth and other planets orbit around the Sun. However, in both models, the orbits of the planets were made to be perfect circles. This may have been influenced by the belief that God was perfect, which led to believing that the orbits should be perfect as well. But this leads to wildly inaccurate predictions for planetary motion. Over time, larger and larger discrepancies would appear between where the planets actually are in relation to an observer on Earth and from where their models would say they should be. So these early heliocentric models made horrible predictions for planetary motion. The geocentric model, on the other hand, could give very accurate predictions out to several decades in advance. There were some corrections that would need to be made periodically, but these were known about and could be accounted for. And so, even though it was a less accurate description of reality, it gave better predictions for the universe. And this is because, for the geocentric model, the main focus was on being able to make accurate predictions for the movement of celestial bodies from an observer on the Earth. The geocentric part was already assumed to be true, so any new observations could just be made to fit with this model. This is largely due to an observer bias, where from an individual's perspective, they are at the center of everything that they can see around them. So when looking out at the night sky from here on Earth, it's rather easy to make the assumption that humanity is at the center of the universe. So for thousands of years, the main preoccupation with people making observations of the sky was to improve their ability to predict how the stars and planets moved across the night sky. Figuring out the true shape and structure of the universe was a lesser concern, because it was already assumed that the Earth was at the center of the universe. How and why were just matters for debate. But because the main preoccupation with these models was predictive power, they were able to achieve a pretty decent accuracy. By the 1st or 2nd century, in some places it was even possible to make machinery that could predict astronomical events several decades in advance. And so even though the early heliocentric models were a better description of the universe, they had worse predictive capabilities. And even though the geocentric model was worse at describing the universe, it could make much better predictions. But only from a human's perspective of the night sky from here on Earth. And this is the problem that I think the standard model has. It's undeniable that it gives very accurate predictions about the universe. However, I think that the underlying theory is flawed and that it assumes that the measurements that physicists take are an absolute reflection of reality. Instead, I would argue that these are just measurements taken from someone at this scale, using these tools to take a measurement in a particular way that leads to a certain kind of result. Physicists are still studying real phenomenon and coming up with accurate models for their behavior, but the models wouldn't accurately describe the physical reality of the universe. Instead, it centers the universe around the perspective of the physicist. It's only true of the perspective of a human at our scale on Earth. Just as with the geocentrists of the past, they were studying real phenomenon and working on models to make accurate predictions of the behavior of those things. But this was only accurate from the perspective of someone here on Earth. Which leads into the second lesson that should be learned from the history of the heliocentric model. That for science to progress, scientists must kill their gods. What held back the models of Copernicus and Galileo was, in part, their belief that a god was in charge of the motion of the planets around the sun. Since God is assumed to be perfect, it was believed that the universe should also be perfect. This meant that the orbits of the planets should be perfect as well. This was later corrected by Johannes Kepler, a contemporary of Galileo, who used the most accurate measurements of the planets to mathematically chart their orbits. And he found that the planets orbit in ellipses around the sun. Kepler also believed that a god was directing planetary motion, but he thought the orbits should encompass all the perfect shapes, not just circles. He changed his mind, however, when he saw the data, and worked out that the orbits were very clearly elliptical in nature. Nonetheless, Kepler still believed that a god was directing the motion of the planets, even if their orbits were imperfect. Because what else could be holding up the stars and planets? This thinking stopped in the time of Isaac Newton, when gravity was finally described as the force that kept planets in motion. This discovery led, in part, to Newton no longer believing that a god was directing the motion of the planets. However, he was still sure that a god was directing life on the planet Earth, which was widely believed until Charles Darwin was able to describe the evolutionary process that created the diversity of life. All of this is to say that there are times when scientific progress can't be made unless or until the gods and other supernatural phenomenon are removed as an explanation. Which isn't that religious people can't do science, as the vast majority of all scientists, as well as the naturalists and philosophers before them, have held some kind of religious belief. For example, not only was Kepler religious, but so too were most, if not all, of the people who created the data that Kepler used. And this built into a substantially more accurate model of the solar system. So research in science can be done with religious intent. What I'm saying is that progress in science can't be achieved until supernatural explanations and reasoning are removed. And this is a problem I think that physics still has, where the field still has a god that it needs to kill in order to make progress. That god being the perspective of the physicist. I know that most physicists would say that they don't consider themselves gods, but that's not what I'm saying. Well, not entirely. The point is that written directly into the Standard Model is that humanity is at the center of the universe. All of reality swirls around the physicist, which is a similar problem to what created and maintained the geocentric model. With the tools available, it did kind of look like humanity was at the center of everything. Something commonly bolstered by a religious belief that people really were the center of all things. And I think the same problem still plagues physics. With the tools available, it does kind of look like humanity is at the center of everything. Something commonly bolstered by a belief in the power and immutability of the physicist perspective, and sometimes also by a religious belief for some people. So when physicists find that there's a limit to what they can measure, this is taken to mean that the universe itself has definitive limits, and that the universe becomes finite and small, with humanity at its center. This may sound like an exaggeration, but there are groups of physicists creating their own theories about how they directly control and manipulate the fabric of the universe. There's the multiverse theory, where the decisions or actions made by a physicist actually create new realities. Each decision they make creates new physically real parallel universes. Or simulation theory, where it's believed that it's possible for a physicist to someday perfectly model the universe such that a being living in the simulation couldn't tell that they were in a program. And because of this, we might be living in a simulation now. And then there are the many theories that just flat out state that the thoughts and actions of physicists create and bend reality around them. All but coming out and saying that physicists are as gods, that they create reality. Of course, none of these ideas are a part of the Standard Model, and not all physicists support such ideas. These are interpretations that only some physicists hold that fall well outside of proven fact or even consensus opinion. However, the fact that these kinds of interpretations are taken seriously by groups of physicists should mean something. That they are all just picking up on the fact that the Standard Model centers the universe around the observations made by physicists. Because at its core is the idea that the measurements and observations taken by physicists perfectly reflect reality. It's just taken for granted that, of course, the physicist is at the center of the universe. So even if the other interpretations can be seen as fringe, I would argue that they reflect a broader problem with physics. That the Standard Model is centered around the perspective of the physicist. It does not try to address or question the bias of the observer. Because if the universe really does have an infinite scale, then we are not at the center of anything. Our perspective is just limited and biased. The universe does not care if we can measure or understand it. We just sort of exist and have access to what is available to us due to the properties of nature. Which is why I think physics can only be improved by killing its god. The perspective of the physicist at the heart of physics. Or at least, I think that some insights can be found by simply considering observers at different scalar locations. I'd like to briefly talk about Roger Penrose and his model of cyclic cosmology, as it's a good demonstration of what I'm talking about, where even good and respected physicists can't help but center the universe around humanity. When doing research for this series, I went looking for physicists who had any opinions on the universe having an infinite scale. I found very few who even acknowledged the possibility, and those that did almost always immediately dismissed it out of hand. Which is why I was so excited when I first saw Penrose's model of cyclic cosmology. Here was a well-respected physicist promoting the idea of an infinite scale to the universe. However, that excitement turned to disappointment very quickly once I heard the details. Basically, other larger or smaller scale universes could exist, but they would be separated by time and scale. So while the universe may be infinite with an infinite scale, there is still a definite floor to everything, where there's a smallest, most fundamental thing in the universe, and where there's also a limit to how large structures can be. Penrose's idea came from thinking about the end of the universe. One possibility is the heat death of the universe, where matter continues to spread out from other matter due to expansion, and after some vast amount of time either decays or becomes some stable, possibly inert matter. According to Penrose, if the universe has an infinite scale, then eons after the heat death of the universe, at some larger scale, the conditions would be similar to those at the smallest scale in our universe just before the Big Bang. So after our universe ends, another could be created at some larger scale. And this process could have happened countless times before our own, where our universe was not the first, just one of many. And after the universe that follows us ends, it too will be replaced by another universe at an even larger scale. And this is the cyclic cosmology model, a universe with an infinite scale and an infinite number of universes. But these universes exist at different scales and at different times from each other, such that each universe is created from the one before it and creates the one after it. This was seen as a radical idea, a universe with an infinite scale and an infinite number of universes. I wanted to like it. However, it puts humanity at the center of the universe. I know it looks like this minimizes humanity, makes us one small part of a much larger indifferent system, but that's not how this model is structured. At its heart is the idea that even though there is an infinite scale to the universe, nothing exists in space and time except for us. The only scales of the universe that have anything within them are those which physicists are currently aware. Penrose appears to believe that there is a smallest possible size to reality, and apparently that there are limits to how large in size structures can be. What this means is that at larger and larger scales above our own universe, there would be nothing. According to Penrose, even if there is an infinite scalar dimension, almost all of it is empty except for the small range of reality that we exist within. Above and below our scale, there would be a vast emptiness through all of infinity. This, despite the fact that his idea rests on the fact that empty regions of space at larger scales are equivalent to the quantum scales before the Big Bang. Which means that at some larger scale, under Penrose's own idea, it should be possible to get to a scale so large that the influence of matter from our universe is indistinguishable from that of empty space. And so it should be possible for another large-scale universe to coexist at the same time that our universe does. This should also be true of scales smaller than our own as well. And since the scale of the universe is infinite, infinitely many universes could conceivably exist, which would make it one of the possible models of the universe described in the fourth video. But that's not what Penrose argues for. Instead, his idea is that we are special in all of reality, that only our universe can exist, that only we can exist. What physicists know about and can see encompasses all of reality. But not only that, the entire infinite scales of the universe must wait patiently for what we are to completely stop existing before anything new can be created. And once our universe does stop existing and finally permits something else to be created, then the scales that our universe once existed within will forever be left alone. It will forever be our gravesite. Nothing else can ever be created on top of our final resting place. The universe must leave it alone as a monument to our once great and mighty past existence. Even in death, the universe will never forget us and never replace us. Basically, Roger Penrose couldn't help but center the universe around the observations of the physicist, because even the most radical ideas to come from physics can't help but put humans at the center of everything. If any ideas in this series turn out to be worthwhile, then all Roger Penrose would have needed to do to come up with them himself was to think of the cyclic cosmology model from outside the human perspective. Because that one change would have opened up a lot of questions. Like, how would the experience between two observers at different scalar universes compare to each other? Or, if there are infinitely many smaller scales, then what are quantum fields exactly? But Penrose has the mindset of a physicist, where the physicist is at the center of the universe. He couldn't think of a universe beyond the human experience here on Earth at our scale. In my opinion, one of the biggest mistakes in science occurred when physicists collectively decided that there was a floor to the universe, that only what physicists could observe could exist, that their perspective is absolute because they were at the absolute center of the universe, that they could be as gods. The biggest flaw with this idea is of course that it lacks any evidence or a working model to make predictions. Which means that even if you found this series convincing, it's still nothing more than pure speculation. So I'll discuss a few ways to move forward with this idea. To start, it should be possible to describe dark matter in galaxies as the movement, distortion, and interaction of space-time caused by a galaxy's star systems and black hole. If this is possible, and successful, it should help define some more properties of space-time and the physical limitations of motion within it, which should lead to a theory of general relativity that not only describes the warping of spacetime because of the presence of mass or energy, but in how spacetime fluctuations spread and interact with each other to influence matter and energy. If it reaches this stage, then this work should be expanded to other scalar phenomenon, starting with trying to describe the movement of galaxy clusters and the creation of galactic filaments. And then this model would need to be able to describe particle behavior in terms of fluctuating spacetime, basically using general relativity and the movement of spacetime to describe electromagnetic waves. A gravito-electromagnetic theory, if you will. This should go some way into progressing towards describing the universe in 5 dimensions. A model of how the movement and interactions of smaller scale objects create the structures and properties of the scales above them, as these smaller scale objects experience more time relative to larger scales, where the universe is a dynamically moving 5th-dimensional fluid with space-time as its medium. And if somehow this idea can make it that far, then it might be possible to start speculating about what lies beyond the observable universe. Of course, with increasing levels of uncertainty the farther away we try to imagine beyond what we can directly see and measure, at least if this idea actually has any merit and works at all. As for actual experiments that can be run, I have 2 in mind. One would be what I described in the first video, where it should be possible to run any Bell's inequality experiment with 2 photons created from independent sources that go through separate experimental setups, but are polarized at some step along the way. Particles run through such an experiment should still violate Bell's inequality. If this works, then it would demonstrate that you can get correlations that are as strong as quantum entanglement without the entanglement, because the 2 photons never interact, so it couldn't be entanglement that is causing these results. The local interpretation would just be that the history and state of the photon itself is enough to explain quantum entanglement. The second experiment wouldn't necessarily prove locality or disprove non-locality, it could only put constraints on any future hypothesis. This would be a modification of the Mach-Zehnder interferometer. In this experiment, one apparatus is set up normally. However, right before where the block is set, a path can be opened where a photon will be redirected to a second apparatus. This secondary setup consists of a second source of photons that sends them down a path through a polarizer towards a beam splitter that splits into 2 paths towards 2 separate detection plates. So the photons from this source are on a single route until right before the detectors. The redirected path from the first apparatus would lead the photons towards the beam splitter of the second apparatus. The design should be such that a photon from the first and second source would arrive at the detection plates at the same time, whether the first photon is detected in the first apparatus or the second. The polarizer in the second setup is used to ensure that any particles from this source are in phase with any particle that it may interact with from the first device, such that they will cause interference in each other's wave function. In this experiment, when there is no block or redirected path in the first apparatus, it should behave like a normal interferometer test. With the second apparatus, the photon would hit either detection plate with a 50% probability, because it isn't interacting with anything. When the block is in place and the redirected path is open, there's a 50% chance that the photon from apparatus 1 goes to the second apparatus. When this happens, at the beam splitter the two particles interact and two particles are detected. In the first apparatus, nothing would be measured. What is of interest is what happens the other half of the time when photon 1 is measured in the first apparatus. In the interpretation I have described, a packet of space-time fluctuations would be sent down the redirected path. This would then reach the second beam splitter at the same time as the second photon, and they would interact. If they're in phase, this should cause interference in the wave function of the second photon, and it should always head to the same detector. Since there's nothing to interact with photon 1, it should be measured at either detection plate 50% of the time. As for a non-local interpretation, at the first beam splitter, photon 1 is split into two superpositions that go down both paths. The second photon is just in a superposition of all possible measurement outcomes. At beam splitter 1, a single superposition from source 1 arrives, but at beam splitter 2, a superposition particle from source 1 and 2 arrive. What should happen next depends on how one interprets what happens during entanglement and the wave function collapse. If the superposition particle from the first device can interact with the photon from the second device, then they should interfere with each other's wave function and particle 2 should always be detected at the same measurement plate. The question here would be what happens to the photon in device 1. If the wave function collapse of the superposition particle in the second apparatus still affects the wave function of its entangled partner, then this could result in the photon always being detected at the same measuring plate, as if it was still directly interacting with it, which would be a clear sign of entanglement and non-local behavior. If collapsing the wave function of the superposition particle doesn't affect the first photon, then it would result in it being detected in either measuring plate 50% of the time. But this would mean that there are constraints on entanglement, because while this superposition particle could interact with and affect another photon, it couldn't transmit that information back to its entangled partner. It would also match the predictions for locality. But if the superposition particle can't interact with the second photon, then both particles should be seen at either measuring plate with a 50% probability because there's no interaction to change behavior, which would put constraints on what the superposition particle actually is. So this experiment can be used to rule out or support this kind of local model, but it can only be used to constrain non-local models, as the results could be interpreted to support a number of different possibilities. And so that was the interpretation of physics that I came up with from pursuing a 15-minute idea about how time should be relative between different scales of the universe. I would like to continue to create videos on my thoughts and ideas about science and nature and whatnot. However, I currently work a full-time job and can only do this in my spare time off. If you'd like to see me do more videos, then please consider donating. If I can get enough support, I would of course like to do this kind of thing full-time. In the future, I would like to cover more topics in biology. I would really like to do a series on intelligence and consciousness, as that's what I have the most thoughts on. But that's going to be an even larger project than this, which took bloody ages to complete. So I'll most likely try for ideas that are smaller in scope for a while. Anyway, thank you for your time in watching all of this. I do hope you were entertained, or at least found this mildly interesting.